All right, so you have a cylinder rolling down, and it's rolling without slipping. And the center of mass acceleration, if you guys look up the expression, it's g sine theta. Theta is the angle of the incline. It's g sine theta divided by 1 plus I center of mass. That is the moment of inertia of the object about the center of mass of the object divided by mr squared. Okay. And this center of mass moment of inertia is some constant times mr squared. And in the problem, what we want to do is find this constant. Okay, so let me show you some moments of inertia. And there's a table like this in your notes in chapter 10. So for instance, for this guy, and in all these cases, the mass is uniformly distributed. Okay. So in this case, the constant is a half. So for a uniform cylinder, for a solid sphere, like a bowling ball, it's 2/5. Okay. For this rod, it's 1/12, and so on. Yep.
Are these easy to memorize, or?
No, you don't have to memorize anything in my physics class. Yep. Yep. All right. Now let me ask you this. How would I make this number half bigger? What could I do to make it bigger? What would I have to do to make? I'm sorry? No, I can't hear you. So how would you make that constant bigger? So if you see the formula for the moment of inertia is MI/RI squared. Okay. So R is the distance from the axis of rotation. And so you want to make this greater, you make this distribution greater. So if you have a solid disk, if you put more mass toward the end, toward the edges, that's how you make that constant bigger. Okay. Anyway, so that's what the problem is asking you. Okay. So if this were a uniform disk, okay, a rigid body with a cross-sectional area it rolls. Okay, so we'll find this constant. Okay, so there's the center of mass acceleration. Okay. Now they tell you that the object starts at rest and it covers 10 meters in 2.6 seconds. Okay, so we'll choose this direction as our x-axis. Okay, and x minus x naught is v naught t plus 1/2 at squared. This is 0. It starts at rest. We know the time of roll. We know this is to be 10 meters, so we can calculate a. Okay. So a is 2 times x minus x naught divided by t squared. Okay, so that's the acceleration of the object. Okay, so the acceleration of the objects of the center of mass is 3 meters per second squared. Okay, and we'll plug it in here and calculate this. Okay, so we get 1 plus I center of mass divided by mr squared. Okay, I center of mass divided by mr squared is this constant that we're trying to find. Okay, so that is equal to so I center of mass divided by mr square equal to g sine theta divided by a minus 1. Okay, so we brought the 1 over there. That's the constant that we're looking for. All right, so let's plug these things in. 9.8 sine 30 divided by 2.96 minus 1. All right, so it's that which is roughly 2/3. So let's see. 2/3, which, okay, so it's probably a thin spherical shell. Okay, that's the object. And you guys understand from this formula, the greater this constant, the greater this constant is, the bigger this number will be, the smaller the acceleration. Okay. All right, this problem says a solid cylinder rolls up an incline at an angle of 20 degrees. If it starts at the bottom with a speed of 10 meters per second, how far up the incline does it travel? Okay. And again, the acceleration is the same formula as before. The acceleration is in the opposite direction. So the acceleration is, and they tell you it's a solid cylinder. Okay. So and you guys can look up I center of mass is 1/2 mr squared for a cylinder. And again, you see here's the center of moment of inertia, but the center of mass is 1/2 mr squared. Yeah. So the acceleration is g sine theta, and 1 plus a half is 3/2. So this would be 2/3. Okay. There's the acceleration. So now we want to calculate how far up the incline does it travel. So again, we'll label our x-axis in this direction. Okay, so x minus x naught. All right, how about we use this formula? Let's use v square equal to v naught square plus 2a x minus x naught. X minus x naught is what we want to find. A is given by that. We know A, it's a 20-degree incline. Oops. Final velocity is 0. Initial velocity is 10 meters per second square. 10 meters per second, okay. So x minus x naught is v square minus v naught square divided by 2a. Final velocity is 0. 10 square divided by 2 times 2/3, 9.8 sine 20. And the acceleration, by the way, is negative. See, this was in the positive direction, acceleration is negative. So $22 meters, which is roughly the width of this room. Okay, so, and 10 meters per second, do you guys have any sense of what that speed is? That's how fast Usain Bolt runs. That's 25 miles an hour. So if you roll a cylinder up start the cylinder up at that speed, it'll go an incline. If you have an incline from that roof to the bottom, it'll reach the top. Okay. All right. At a particular instant, a 1 kg particle position is r is that. Its velocity is this. And the force on it is that. What is the angular momentum of the particle about the origin? Okay. So if a particle has a momentum like that, and if you want to calculate the angular momentum about the origin, angular momentum is this vector. It's r cross p. Okay, so it's the cross product of those two quantities. And what is p? It's mass times velocity. Okay, so the mass of the particle is given here is, okay, now here in this formula you can see that the angular momentum can be calculated about any point. So this angular momentum is calculated about that point. There's nothing special about that point. You can calculate the angular momentum about any point. You just need a vector from that point. Okay? So you're calculating the angular momentum about the origin. Okay? And so this problem is about calculating a cross product. Yeah. So its mass is 1 kg, and the position vector is 2i plus 4j, minus 4j. Plus 6k cross v. So momentum was mass times velocity. I've already multiplied mass. So velocity is minus I plus 4j plus k. Yeah. And the units are, well, the mass is 1, and the units are kg meters per second. Kg meter square plus per second. Okay. So you get kg meter per second from here, and then another meter from here. Okay. All right, so now it's just a matter of finding these cross products. All right. Again, you can do the cross product any way you like. But let me remind you, I cross j is k, and the opposite j cross I is minus k. J cross k is I, and so on. Okay, so that's the how you, if you remember the cross products, I cross j is k. Okay. Here is a okay. So I cross j is k, j cross k is I, k cross I is j. Okay. If you go in the opposite direction, you get negative signs. I cross k is j minus j, and so on. All right, so let's do this cross product. Where is my lasso tool? All right, so, okay, I cross I is 0. I cross j is k. So 2 times 4 is 8. I get 8k. Then I cross k is minus j. Okay, so that's minus 2j. And then j cross I is minus k. J cross I is minus k. Yeah. So j cross I is minus k, and minus times minus is plus, so it's minus 4k. And then j cross j is 0, j cross k is I, so that's minus 4i. Yeah. And then the last one, k cross I, so let me bring this. So k cross I is j. K cross I is j, and there was a minus sign, so minus 6j. K cross j is minus I, so that's minus 24i. And then k cross k is 0. K cross k is 0. All right, so now we can add everything up. So here's the angular momentum. Okay. So i's, that's minus 28i. And minus 8j. And that's 4k. And what are the units again? Okay. So that's the angular momentum. And again, like I said, you can calculate the angular momentum about any point. R is the vector from the point to where the particle's momentum is. Okay. So you can calculate the angular momentum about any point. What is the torque on the particle about the origin? So there's a force acting on this particle. And the torque we'll calculate the torque about the same point. Okay, and again, it's a cross product. So torque is R cross F. Okay, so for a problem, if you're calculating the angular momentum about a given point, you want to calculate the torques about the same point. And then Newton's second law will be good. What is Newton's second law for the rotational motion? What is torque is dL by dt. This is the parallel of Newton's second law, where force is dP by dt. Okay? All right. So this equation is good as long as you calculate the angular momentum and the torque about the same point, and that's what we're doing in this problem. Okay? You can't calculate the angular momentum about one point and calculate the torque about another point, and then that equation won't be good. Okay? And that makes sense. All right, so let's calculate the torque. All right, what is the force? Force is 10I and 15J. Okay, so 2I minus 4J plus 6K cross 10I plus 15J. Okay. So and I'll do this a little quicker. I cross I is 0, I cross J is K, that's 30K. By the way, so, well, okay, so let's do that. And J cross I is minus K, but there's a minus here, so that's plus 40K. Yeah. And then J cross J is 0. K cross I K cross I is J, so that's plus 60J. And then K cross J is J cross K is I, so K cross J is minus I, so that's minus 90I. Okay, so the torque is minus 90I plus 60J plus 70K. And what are the units for torque? Look at the formula. Newton meter. Okay, so they ask you in part C, what is the time rate of change of the particle's angular momentum? So it's 90I. It's equal to the torque. Okay. All right. You guys understand? All right. So you have to get comfortable with doing cross products. Okay, this problem says a pulsar is a rapidly rotating neutron star. What is a neutron star, by the way? You guys know what a neutron?
Bunch of neutrons.
Right.
It's like it was a star.
Mm-hmm.
I think it's still in its life.
What's that? Yeah, you're right.
It's a bunch of neutrons.
Yeah, it's a bunch of neutrons. So this is the notation for our solar mass. This is the mass of our sun. Okay, that's the notation. And the mass of our sun is about 2 times 10 to the 30 kgs. Okay. So our sun is a sort of a blast star. Now, our sun will die in about 5 billion years, and it will become what is called a brown dwarf. Okay, so if the mass of a star is less than 1.4 times the solar mass, then it'll become a brown dwarf when it dies. What do you mean when a star dies? What does it mean? I'm sorry? Yeah, so eventually after it's run out of fuel and stuff like that, it'll die. Supernova is one of the ends. Okay. If a star is, its core mass is between 3 solar masses and 1.4 solar mass, okay, then it becomes a neutron star, and essentially, like our friend here said, it's all neutrons essentially. Okay, and if a star's mass is, the core is greater than 3 solar masses, then it becomes a black hole. Okay? So you have to be this heavy to be a neutron star, between 1.4 and 3 solar masses. And the person who discovered these, Miss Jocelyn Bell, she's come to town several times. She's come and spoken at Embry-Riddle several times. Okay. And when a star becomes a neutron star, so our solar radius is, our sun's radius, again, I don't do this every day, so I might be wrong in some of the numbers. The radius of our sun is about 700,000 kilometers. You can Google it. And if it became a neutron star, its radius would be about, let's say about 10 kilometers. Okay. So that's almost 100,000 times smaller. Becomes 100,000 times smaller. Okay. So the density would increase by a factor of 10 to the 15. Okay. So it essentially becomes a big, large nuclei. Yeah. You guys have seen, you guys have watched skaters, right? They start spinning and then they'll wrap their hands and legs around themselves. And what happens? They're spinning faster. Same thing happens with this thing. Now imagine this, you wrap yourself to a size 100,000 times smaller. Right. So you're spinning fast. Okay. So here is a massive object spinning about 1,000 times a second. Yeah. Okay, it's spinning very fast. Yeah. Okay, so here's the question. Yeah. All right, if the solar system were this big, the size of this room, I remember I bought that model, and if the Earth and Sun is this far apart, the solar system is that far apart. So Neptune would be at the end of the room. It's very hard to see Neptune in a telescope. You need to know exactly where to look at, even with a powerful telescope. The closest star is near Miami on this scale. Okay. Now, if a neutron star is in New York, and it's the size of a tiny rock, how the heck are you going to see it? It's not emitting, you know. So here's how it was discovered. Do you guys understand the problem? So like I said, here's a neutron star. It's spinning like crazy. Spinning at about 1,000 revolutions per second. Okay. Now, if the neutron star, so it has a magnetic axis, this is the spin axis, and if the neutron star has a magnetic axis like this, okay, it'll emit particles along the axes, along the magnetic axis. I'm just drawing this stuff, okay? So it'll emit beams of light along the axis and particle, okay? And so it's like a lighthouse, and this beam is spinning 1,000 times a second. So imagine this is the spin axis, and here's the magnetic axis, okay? And this axis is spinning 1,000 times a second. And if this axis is pointing at you, then you see a blip 1,000 times a second. If this is not pointing at you, you can't see it. And if this axis coincided with the spin axis, then it had better be pointing and you would straight at you and you would see a steady light, but that would be too dim. This is how you discover neutron star. And now you understand the name pulsar. It's pulsing. Okay. All right. So again, the folks at Riddle are good friends with Miss Jocelyn Bell, so she comes here often. You should go see her.
So if
Mhm.
a neutron star.
And she's funny as hell. Oh man, she's so funny, it's not even funny. Yeah. Mm.
So a neutron star will spin much faster.
And she should have won the Nobel Prize, and she wasn't. Sorry.
A neutron star will spin much faster than its parent star because it got smaller, right?
Yeah, much. Yeah.
What happens with black holes in their spin
Yeah.
when all the mass is concentrated to like
Yes.
because by the reasoning they would spin
Mhm.
infinitely fast, but they're
So-
also a point.
Yeah. So the point is what we are able to say now, but they're not a point. But we don't know what the reality is. Once all the mass drops out inside the event horizon, Einstein says they collapse to a point, but we know Einstein is not right there. But nobody has a better answer. So
It's just kind of unclear.
yeah, it's unclear. Yep. All right, so a pulsar is a rapidly rotating neutron star. And so what is the mass of this neutron star? Between 1.4 and 3 solar masses. Okay. Has a period of, 33 milliseconds. Okay. Radius of 10 kilometers. 10 kilometers is from here to Granada Avenue. So a sphere that big, and look at this, it's exactly 1.4 solar masses. Okay. The pulsar's rotational period will increase over time due to the release of electromagnetic radiation. Like I said, so there it's releasing this radiation, it's spinning. All right, so it's losing energy and it'll slow down. Due to the release of electromagnetic radiation, which doesn't change its radius but reduces its rotational energy. Yeah. What is the angular momentum of the pulsar? Suppose the angular velocity decreases at a rate of that. What is the torque on the pulsar? Okay. So what is the angular momentum of the pulsar? The angular momentum, so If you guys look up, just like linear momentum, mass times velocity, angular momentum is moment of inertia times angular velocity. And for a sphere, the moment of inertia is 2/5 mr squared. So for a solid sphere, oops. What happened? Okay. Yeah, so for a solid sphere, it's 2/5 mr squared. Okay. The mass is 2.8 into 10 to the power 30 kgs. The radius is 10 kilometers, 10 to the power 4 meters. And angular speed has the period is that many milliseconds. So angular speed is, it rotates through an angle, and you got to do the angular speed in radians per second. So it's 2 pi radians, and the period is 33.5 into 10 to the minus 3 seconds. Okay, so that's the angular momentum of the pulsar. Okay, so we'll take care of powers of 10. Yeah, so you might want to get in this habit. So this becomes positive, that's 10 to the 7, 10 to the 30. Okay, so this is equal to 2/5, 2.8 into 2 pi divided by 33.5 into 10 to the power, what did I say? 10 to the 37. Yeah. And what are the units for angular momentum? This is kilograms meter square per second. Okay. All right, so okay, so that's the angular momentum. And they say, suppose the angular velocity decreases at a rate of 10 minus 4 radians per second squared. What is the torque acting on the pulsar? So the torque is I times alpha. Okay? And we already, we didn't find, okay. And there's alpha, 10 to the minus 4 radians per second squared. So it's 2/5 mr squared times alpha. Okay, so I guess we have to go through those numbers again. 2.5 into 10 to the 30. All right, let me do it on another sheet. Okay, so did I get this right? I didn't square this. So that should be 40. All right, so here we go. This is 30, 38, 24. So Newton meter, and 2 into 2.8 divided by 5. So that's the torque slowing the neutron star down. Yeah. Mm-hmm.
How do you, what did you put your torque equals, you said it or the inertia times the alpha, like how can you, like why did you do that for the torque?
I'm sorry?
Like why did you do torque equals the inertia times the alpha?
Okay, well, they give you alpha. They are giving you the rate at which the angular velocity is decreasing. So they're giving you alpha, and torque is I times alpha.
Oh, okay, I see.
All right, I'll do one more problem. So here's an interesting problem. It's futuristic. So if you read sci-fi, okay, this might interest you. So a space station consists of a giant rotating hollow cylinder of a mass 1,000,000 kgs. Okay. And now this kind of stuff is possible with launch costs coming down dramatically because of Elon, okay, including people, and a radius of 100 meters. So 100-meter radius. Okay, so again, a future space station is like this. Okay. Your apparent weight, see, you don't feel the force of gravity. What you feel is, so when you're standing on the ground, Earth is pulling you down. Earth is pulling you down and the ground is pushing you up. This is your apparent weight. Okay. So if the ground didn't push you up, you would feel weightless. So for instance, you can do this inside a pool. Inside a pool again, Earth is pulling you down, the force of gravity, but there's a buoyant force on you which is almost equal to this. And so now the ground is not pushing you up and you feel weightless. Okay. All right, so it's the ground you're standing on that pushes you up, that's your apparent weight. Yeah. So here's the deal with this space station. Yeah. Do you guys remember what do you have to do to make an object go in a circle at constant speed? What do you need? Is it accelerating? Yes, it is accelerating. The direction of the velocity is changing, so you're accelerating. And the acceleration is a centripetal acceleration. And the centripetal acceleration is v squared by r. Okay. So if you're going in a circle, there needs to be something that's pushing you inward like that. Okay. Now, in in a space station, what you'll do is this is a cylinder. It's like this. So this is the structure. Here's your space station that's going on an intergalactic journey. And you are standing in here. And the dimensions of this is from here to Mainland High School. And this thing weighs 1,000,000 kgs, this structure, as much as 1,000 cars. And how do you produce artificial gravity? I mean, if you got to travel several months, you got to have gravity. You spin this thing. So, and you're standing in here, you're going in a circle, and this thing is pushing you down. And that's how you produce gravity. So all plants will be grown there. They're being pushed this way. The roots will come out like that. So that's the structure. Okay. So you're spinning this way, and there's the gravity. Okay. So what we'll do is okay. So it is rotating in space at 3.3 revolutions per minute. So imagine that structure from here to Mainland High School, and it's rotating at 3.3 revolutions per second. Yeah. In order to produce artificial gravity, if 100 people of an average mass of 65 kg spacewalk to an awaiting spaceship, what is the new rate of rotation when all the people are off the station? Okay, so what happened was 100 people went on strike. They got into a spacecraft and went away. And now what will happen to the space station? So this is a conservation of angular momentum problem. So when you lose all this mass, your moment of inertia is decreased, and so now you'll be spinning faster. Okay. All right, so the initial angular moment of inertia is of the space station plus moment of inertia of the people. Okay. It's the space station consists of a giant hollow cylinder of mass 1,000,000 kg, including people on the station, and a radius of 100 meters. So this entire mass is 1,000,000 kg. Okay, so what we're essentially saying, so the initial moment of inertia is all the mass is at that distance. So the initial moment of inertia is just the mass times r squared. So this is 10 to the 6 times 100 meters squared, which is 10 to the 10 kg meter squared. The final moment of inertia. Okay, now what has happened? What is the mass now? You lost 100 people, and you lost that mass. So the mass has decreased to 1,000,000 kg minus 6.5 into 10 to the 3 kgs times 100 squared. So you've lost that much mass. Okay, that's all. And that's, so you see this is, we'll write it in terms of 10 to the 6. That's 10 to the minus 6 point, okay, so that's 10 to the 6 minus 6.5 into 10 to the minus 3 times 10 to the 6 times 100 squared. And the reason I wrote it like that is now it's 1 minus 0.065. Okay, so Okay, so what I've done is brought out 10 to the 6 out. You have 1, and 10 to the minus 3 times 6.5 is 0.0065 times that. Okay. So there's the and this is equal to 0.9935 into 10 to the 10 kg. All right, so what happened? Okay, so the initial moment of inertia was that 10 to the power 10 kg meters per meter square, and when 100 people walked away, the moment of inertia reduced to that much times that. Okay. So it'll speed up. So omega final, so I initial, omega initial equal to I final, omega final. Omega final is I initial over I final times omega initial. And I initial was 10 to the 10, and this is 0.9935 into 10 to the 10. So 1 divided by 0.9935. Okay. So the angular speed increased by 0.2%. Okay, so it's spinning that much faster, that's all. All right. All right, so